All right, thanks for the invitation. And it's my pleasure to be here to tell you about the HIMAT in Asia project. This is a 3-year award from the NASA Earth Sciences Division, and we're just entering our 3rd year. This is a project that involves a lot of really great researchers. It's just an incredible group of people working together to understand more about the high mountain Asia region. There's about 100 individual researchers, students, and technicians across about 14 different institutes. And our goal is to understand the processes that are driving changes in climate of the cryosphere of all the high mountains that span all the way from the western Tian Shan and the Karakoram across the Tibetan Plateau into Bhutan and Nepal. These are some of the highest mountain ranges on Earth, and they store substantial amounts of snow and ice that their runoff feeds into the water resources, and a lot of the communities living downstream really depend on water from these regions. Upwards of 1 billion people are concerned with what's going to be happening with these water resources now and into the future. And so this is a really unique project. It's highly collaborative. In fact, in the solicitation, there was a specific call for teams to work together, to share data, to intercompare their models. And I'm the science team lead for this group, so I'll be telling you a little bit about kind of the collaboration structure that we're trying to design in this project that we hope is really helping to build these connections and help foster research that might not be something that we could pursue if we were just doing a lot of our own individual work. So I'm going to talk a little bit about that just a bit later. The science that we're focusing on can be divided into 3 main themes. The first is to really understand what is going on with the cryosphere in this region. So we're using things like high-resolution digital elevation models and other remote sensing data sets to get at things like the glacier surface velocities, the mass balance of the glaciers, and the changes in snowpack, the snow-covered area, and the suite. And this is a region that's largely understudied with respect to these cryospheric indices. Field observations are fairly sparse, and the data sharing across these countries is often a little bit limited. And so we're taking advantage of a variety of remote sensing tools. All of that information is being fed into a variety of different water balance and land surface models. And so many teams are doing very high resolution modeling of this area for the first time and taking a lot of the inputs from teams that are building, say, precipitation and temperature grids and running that through land surface models that allow us to reconstruct things like the regional water balance. And that is then combined with things like what we're looking at here, which is the satellite gravimetry data from GRACE for validation. We're beginning to get a really good understanding of the water balance variations in this area, and Batu will be talking a little bit about that later. The overall goal is to bring all this information together to inform decision support in the region, so we can begin to have a better understanding of the frequency of landslides, the likelihood for flooding, the downstream impacts of changes of water resource availability and the timing and magnitudes in the future that affect things like droughts and other downstream impacts on ecosystems. And so we have multiple teams working across these different topics. One of the most interesting animations that I can show you here is coming from our team at NOAA GFDL. This is work of Paul Janou and Sarah Kapnick. This is a GCM model output that's really tailored to look at things like the dust optical depth in the brown and orange colors, which show us the patterns of dust distribution largely being sourced from all the deserts across this area. And then in the purples and dark colors, you're looking at the black carbon optical depth, which relies on information about the pollution coming from many of the industrial sources across this region. That is being combined with the land surface models to understand more about the evolution of the snowpack here in white and blue. And you can see the decay and the growth of the snowpack over 1 year and its response to things like the optical forcings that are being deposited on these snowpacks. We're then linking and coupling all these models together to get a much better understanding of what is the impact going to be of all these atmospheric pollutants on the cryosphere in this area. So it's a really important sort of way that we can improve our understanding of the physics. So all of these components, I've just shown you a couple of slices of this larger effort. Again, it's really bringing together understanding of the meteorological conditions, the land surface states, and then this core modeling component to better understand the physics of the various different cryospheric components, There's a really interesting piece involved with assimilation and reanalysis of the satellite and field observations back into the modeling work. And then the outputs, as I said, are fed into things like economic valuation models, things that we can leverage to understand the impacts on downstream communities in the area. Now, the data sets, for example, the GCM I just showed you, hundreds of gigabytes of data in just one model run. Multi-dimensional data sets that need to be shared across the team for us to do this kind of collaboration work is necessary. And many different groups are producing multiple versions of different models in different formats. And so we have this sort of data sharing challenge, and that's one of the pieces that our team at UW is really focusing on, is how do we build cloud computing solutions and other ways of sharing data sets that will allow us to enhance this collaboration that's really valuable for our work. And this is reflective of what's happening in the broader community. This is the projected data volumes at the NASA DAX distributed active archive centers here in the future. With the coming online of things like ISAT-2 and NISAR, we'll be up in the hundreds of petabytes of data storage. So this is a known issue, and it's something that our team is really grappling with as we move forward in this work. So we're designing ways of working with data in, for example, the NASA provisioned cloud that's called ADAPT. This is where we work with a lot of our raster data sets. Our partners at GLIMS are helping us build database tools for the sharing of time series and vector data. And this is for our own internal sharing. And then when we're ready to distribute this out to the broader public, we can then push this out to the NSIDC DAC for long-term archiving and distribution. So if you go to the NSIDC website, you can see some of our early products that are now being made available. And remember, these are actually being distributed, and it's a requirement of our work that we share this out to the world right away, even before the publications have gone out. And so you can visit this site. And one of our early products here is this high-resolution DEM coming from Worldview and other commercial satellite imagery. And here's just a screen capture of gathering that data on the NASA Earth data site. I want to talk a little bit about some of the collaborative efforts. I know I really appreciate the collaborative nature of this particular team here, IARPIC, and I wanted to just mention some of the things that we're doing around building a team structure that's, commonly we form these 3 or 4 year teams that come together, and we have to very quickly find ways to build connections. And some of the things that we've been trying to enhance that is a very adaptive leadership structure, a way of sort of empowering individuals and smaller groups across the team to make decisions rather than all the decisions coming from, top-down sort of more bureaucratic type of approach. Our in-person meetings are really designed in a way that help enhance building of connections and understanding of the ways that we're sharing our data in a way that kind of respects the integrity of each of the data sets that's being shared across the team. We're using professional facilitators to help guide some of the design of this work. And then we have a number of team web resources that we use to update the team on all the work that's being done across various individuals. Here's an example of us having a discussion around the authorship and data sharing practices that we want to hold to as a team as we think about doing these multi-author papers and sharing data sets that may not be fully formed yet, but we would benefit from having other teams looking at them. So this is a first step in that direction of building some of these collaborative structures. We also, especially here at the UW, are interested in fostering this idea of open source software and building reproducible workflows. So we are encouraging HIMAT to share code on GitHub, and we have this GitHub site that you can visit here to look at the scripts that we're developing to develop a lot of the code and the analysis that I've showed you here. And we also have, as I said, this website that you can visit, himat.org, to learn about what's upcoming with the team and the latest results and data sets being published. I'll just finish by talking about the upcoming events that are occurring here for us. The AGU in DC will be hosting a session C14. We just found out that we have both oral and poster slots to dedicate to our collaborative research topic here. So I encourage you to check that out if you're at AGU. And then one thing we've been experimenting with is smaller group meetings. We're going to have a group meeting around snow products being developed within the group. This is an internal small group meeting, but all of the elements and outcomes from that will be shared on our website. And finally, we just posted a research topic on frontiers in earth science. One of the ideas at our last all hands meeting was to put together kind of a special issue that collects together all of the research results as they're coming in from the various groups. So I encourage you, if you have interest in this or other colleagues that might be interested, to have a look at this research topic and see if you might be interested in submitting to it. So that's all I wanted to say for my piece. I want to turn it over to Batu, and you know, he's a team lead for a group of scientists that are working on many of the elements that I talked about, and their work really exemplifies the collaboration that I've spoken about, really working across teams to leverage different data sets, and I'll hand it over to him to tell you some of the results of that.
All right, thank you, Anthony, for that introduction. Let me get my slideshow shared up on the screen so people can see. All right, I believe you can see. If not, please yell. And I do have the chat window open too, so if you have questions as I'm talking, feel free to type up there, and or if you have questions for Anthony's talk, feel free to write them there, and we'll, I guess, have a Q&A session at the end. So what I wanted to talk to you about was give you a little bit of information about our own project. As Anthony said, I'm one of the PIs that make the bigger HIMAT and Asia team. Our team is also relatively large on its own. We have scientists from NASA Goddard Space Flight Center, University of New Hampshire, and University of Alaska Fairbanks that are specialized in different aspects of this project. In terms of the project's overall goal, what we're trying to do is to investigate the climate, glacier, and hydrology system of the high mountain Asia region as a whole. And we do this by, in 4 steps. First step that we focus on is essentially the climate modeling, which Anthony showed you a good example of the global climate model, which is of course amazing, but we like to be able to see the convective precipitation and the impact of that. So we have a high resolution regional climate model running that is driven by these global climate models. We then use this model outputs and also the remote sensing data sets to sort of quantify and better validate the glacier models and the hydrologic water balance models, again, that Anthony was talking about. And I'll be sort of talking about each of these steps and giving some examples of the work that we have been doing. If we start with the regional climate model, the simulation that we're running, which is a coupled ocean atmosphere model, basically WRF and ROMS simulations, are computationally expensive. It takes about 3 weeks, real time, to do 1 year worth of atmospheric simulation. So we wanted to make sure that we were running the correct parameterization of the model. And here, we have run many different parameterizations. I'm only showing 9 of them in this figure on the right-hand side. And all these figures are run on our original model configuration, which we have 2 nested grids. The outer grid, which you see the entire domain, has a 20-kilometer sampling, while the inner grid, which is indicated by the dashed line, has a 4-kilometer sampling. So while we were investigating the parameters, we wanted to compare the model output, especially the precipitation, because we were concerned about capturing the convective precipitation well with the 4-kilometer model. we compared it with the TRIM precipitation observations. And in this case, we were looking at the 2008 pre-monsoon season between May 15 and June 15. We found out that the results were mostly impacted by the radiation and the intertropical convergence zone. So we actually had to extend our model configuration, which I'll show you in the next slide. And the best configuration after doing all this testing was a certain set of parameters. Like, and another parameter actually that we have changed was the nudging. The default nudging of WRF is about 1 hour, which we sort of wanted the model to run a bit more on its own, and set it to 3.8 days, which gave us the best result in terms of TRIM comparison. And then if you look at the accuracy improvement, what you see in these 9 plots, the worst case scenario and the best case scenario has a 61% improvement. So we reduced the RMSE from 220 millimeters to about 130 millimeters. So it is a significant change, and therefore it was well worth the study, I think. One thing that now, of course, now that we have the parameters, what we're doing is running from October 1999 to October 2015, about 16 years of past historical climate simulations, and we are running this in this new production grid that you can see on the left-hand side, where you can see the extended southern boundary. And we also increased the 4-kilometer nested domain to include the Indus, Brahmaputra, and Ganges completely, so that we can get a better hydrological estimate for those. So what you see on the right-hand side are the 2-year total precipitation and its comparison with TRIM observations. We calculated the accuracy of these observations, which indicates that in the outer domain, in the 20-kilometer domain, we actually have a higher, about 80% validation, while on the nested domain we have about 62% agreement. And partly that is because of the mountain range, the Himalayan mountain range, over which we know the TRIM observations are underestimated. So it becomes a bit of a chicken and egg problem when you don't, when the validation data also has some issues. And that's actually one of the things that I guess we could collaborate with this group, and not only my group, but also the greater High Mountain Asia team are really looking into coming up with different data sets to validate our model runs. In terms of remote sensing, what the latest analysis that we have done is to process the stereo imagery of ASTER data, in addition to the high-resolution digital elevation model that Anthony had mentioned, done by David Sheen. So David has also been an instrumental team member for us, even though he's not really officially on our team. I think he's almost an honorary team member for us. He and Paul Montesano from the team processed about 28,000 imagery from between 2000 and 2018 with cloud cover less than 50%. And what you see on the right-hand side is the trend in terms of height change, elevation change from this data set over the entire 18 years. And you greatly see a loss of elevation in most of the areas as indicated by the red. Here is a zoom in version so that you can get a better taste of the product. So we don't only see the areas of, that we don't only see that the elevation change, but we can also distinguish the ablation and accumulation zones for individual glaciers. And of course, there is still some noise involved in this data set, but we are relatively happy with these results. And we can, of course, David Sheen went ahead and we can calculate from these volume changes the mass balance for individual glaciers, and we can combine them for some region that we define, and which one of the results you're seeing here. And the results are sort of in it's similar to what the previous publications have suggested, that we see most of the losses in the southern part of the Himalayas, while in Karakoram we sort of have a almost no change, or maybe some areas with gain, and that tends to be the result that people are getting with similar analyses. So the volume change and mass balance change will be going into our glacier evolution model for calibration, which is a model developed by the University of Alaska Fairbanks team by Regina Hock and David Rounds, where these model essentially uses the glacier data from Randolph Glacier Inventory, for example, and the climate data from the either the global or regional climate models, and outputs a glacier evolution, which we then check with the calibration data, similar to this remote sensing observations, that either from David Sheen's high resolution or the ASTER products, and come up with model parameters that we correct until the model is accurate. We then we do it on a select number of glaciers so that we can actually validate our results. So we transfer the parameters to the region and run. We can even then, once the model is calibrated, we can run the future projections with this approach. In terms of typical outputs or this process, so on the left-hand side of this, what you see is the geodetic mass balance, actually an example of the high-resolution imagery that David Sheen had processed to estimate the similar DHDT, elevation change, mass balance figures, which were then used to calibrate the model. And what you see in the middle column is essentially the factors, the adjustment factors in the model, showing you the change in precipitation factor, temperature bias, and degree day factor. So these are essentially not only account for the model and model errors, but also can account for potential errors in the input data. So it is a combined correction. What you see on the right-hand side is typical model outputs that we expect to get, both volume runoff and mass balance changes over time. And finally, we get this climate outputs and glacier outputs and other observations that we put into a water balance model, where we can see the glacier runoff coming off the glacier, which is of course informed by the glacier model. And we can track this water source as it goes into the river basin, and how it is used along the river in terms of farming activities or other horizontal distribution. Eventually, we can also see what the amount of glacier water, glacier meltwater, glacier runoff coming out of the river basin. So what you see on the figures at the bottom are essentially the outputs of glacier runoff. In blue, it is all the water that's coming into the basin, and in red, what comes out of the at the mouth of the river for Indus, Ganges, and Brahmaputra. And as you can see, for some basins, most of the glacier water is already taken up by the agricultural activities upstream of the river mouth. So that obviously has some implications with sea level rise. Here is a final slide that I would like to show you of these results that you were seeing in the earlier slide, but in animation form. What you're seeing is the 1980 full year at a daily scale with the and how the glacier melt in rivers is being distributed. As you can see that the amount of water is changing as the seasons change, which is truly expected. But one thing that I wanted to show you here is that, or mention before I conclude my talk, is that we can actually distinguish glacier melt from snow melt, even though I'm not showing you the example here in this in this presentation. This is a unique capability of the water balance model that University of New Hampshire is running for us. So we can actually track the sources, of course, with some uncertainty. With that, I'll thank you and take any questions you may have.
Great, thanks Batu and Anthony. Those are both pretty fascinating talks. Does anybody have any questions for these guys?
Yeah, Batu, this is Billy Armstrong. I had a question on that slide you were just showing and the animation. I might have missed it, but how do you actually model the agricultural use of that water, or things like infiltration into groundwater systems or things like that?
Yeah, so that's a very good question. So in terms of the agricultural use, what we look at is the FAO data. And obviously, that might be wrong in terms of, the crop type or the area. But, that's one uncertainty that we take. The other is that we have which is one deficiency of the model, which the University of New Hampshire group is trying to address at the moment, is that the groundwater resource is unlimited. And in one of our collaborative activities within the High Mountain Asia team, we work with Isabella Velicogna from University of California system, UC Irvine, to use the GRACE measurements to actually, constrain the total water storage and essentially put a limit on the water balance model. So this is, ongoing improvements. And in terms of the infiltration and other horizontal types, that's basically the water network that's designed using partly the soil type, partly the elevation model by University of New Hampshire, and that is a static layer at the moment. And I don't think that is going to change, but that's also one of the uncertainties we have. So definitely big caveats, but at least it gives us one result that we would like to validate with observations, of course.
Cool, thanks. Yeah, that's really awesome stuff.
Thank you.
Hi, this is Hailong Wang from Pacific Northwest National Lab. I'm wondering about in your snow and glacier model. Do you also consider impurities, impact of impurities on the melting?
So yes, we don't have a black carbon layer if you're asking that, but the model accounts for debris cover. And we do have different melting based on the debris cover percentage of the glacier. And partly that is one of the things that that the calibration procedure is hopefully bundling in the error. Like for example, if we have the black carbon wrong, we will increase the degree day factor to melt a bit more so that we validate the with the observations, with the past observations. So that is, obviously it is not a perfect solution, and what we do is a simplification, definitely, but it is one way that we found out that we could tailor these parameterizations to specific glaciers, and also we could run these large simulations over the entire region and provide regional estimates efficiently. If you look at individual glaciers, our results might be wrong. That is definitely true. But we believe this, statistically speaking, the regional estimates will be on par.
And the further question is about when you evaluate against observations, do you look at bare glaciers and snow-covered glaciers separately, or all them together?
Yeah, so that is also a good question. So when we are looking at the analysis, we actually we did the analysis in two ways. We originally looked at only the summer digital elevation models, for example, for the ASTER imagery, which we sort of took it as a proxy as mostly snow-free, which is obviously not true in all cases. And then we added the winter data and looked at it, and we didn't see a big change in terms of the noise or the long-term elevation change rate. Therefore, we decided to combine the two stacks to obtain a a more fuller data set, which gives us more statistical information about the potential errors per pixel.
All right. Thank you.
Thank you.
Anthony, I have a question for you about cloud computing and GitHub. I think it's fantastic that HIMAT is is requiring investigators to put their data sets up so quickly and in the cloud too, because that enables then they're off of just someone's computer, which is inherently a more collaborative thing. And then GitHub as well. I used to be a big user of that. NASA makes that a little harder. But I'm wondering, one of the common investigators' concerns when they're thinking about sharing their data sets and codes, especially so early in the process, is that, for example, someone might misinterpret them. So separate from the issue of, getting scooped, it seems like, HIMAT is beyond that type of issue. But how did you get the various teams to get keen on the idea of just putting their products up immediately on the cloud, putting their code, presumably however rough it might be, up on GitHub? Was there a specific strategy you took there?
Yeah, that's a great question, Joe. Part of it is that building of trust across the team early on and the building of communications. And I talked with especially the folks running the GCM models that was a major concern for them. They've had difficulties in the past where people take an output and don't really know that it wasn't quite meant for that use that they're trying to apply it to. So one of the things was, for every model, we encourage teams to put up a full metadata description of all the variables that they'd be working with, and then really clearly have other teams understand the implications and the uses of those products. And also, one idea we had that didn't get fully implemented, but was just to have people sort of officially sign off on, if I'm going to be using these data sets, these are the foundational agreements that we have on how it gets used and so on. So those discussions, at least we had early on, and it's just an ongoing thing. I think if I was spinning up this team again, I would really make sure that there was that sign-off process, like more formally, but at a minimum, at least we started to have those conversations, and I think there was enough of that where the connections were built, where people, didn't encounter some of those challenges that often occur. But we're certainly not fully there yet. I mean, I think we've just made some small steps in that direction, but you're totally identifying a core challenge of this kind of work, is to really make sure everything's clearly explained before people take something and run with it.
So do you think professional facilitation of meetings help with that? And also, correct me if I'm wrong, you're the project scientist for HIMAT as a whole. So having also a project science office for such a set of projects, was that particularly helpful? Or was it, do you think, professional facilitation, or just raising it early on, as you mentioned?
I think it's all of the above. I really think that now that I've been doing this is the first time I led a team of this magnitude, and it's clear to me, if you really want to foster deep collaboration, that you actually need an administrative team that spans a number of roles that I tried to fill early on, in just small ways. One is just a science team lead, somebody who thinks about the connections between all the science components. Another is a person just to do project management and logistics and setting up meetings and all the communication channels. Another would be a data facilitator. And another would be these professional facilitators who actually help us design ways to shift our interactions a little bit beyond a 3-day meeting of just talks. So there's not enough opportunity for actually connecting and discussing things. So I think it's all of that. I'm actually interested in writing up something around what I think would help foster collaboration when new teams like this are formed. If you really want to invest in that, here's kind of the minimum that you need sort of administratively for that to happen.
Absolutely. I think that's a fantastic idea. One last, more scientific question, at least from me, is listening to Batu's talk and just, thinking about the Arctic as we do in Antarctic, it seems like one way that these ideas and the specific tools and models could get potentially exported is in better mapping the ongoing wasting of the glaciers in the Canadian Arctic archipelago. I mean, especially when you have so many glaciers, both in high mountain Asia and in the Arctic, separate from the Greenland ice sheet, which often occupies a lot of people's attention. But is there any momentum toward a group doing that sort of once HIMAT concludes? Not that the work will be done, but then to take those concepts and apply them to the Canadian Arctic archipelago as well? Or
yeah, I would hope so. I mean, I'll say a few things and let Batu speak as well, but I would say, we've learned a lot through this process about the ways in which we model mountain glaciers, the role of debris cover. Some of the teams are actually formally looking at how to integrate in the atmospheric chemistry piece into the albedo parameterization. So I think we'll leave this work, or will be ongoing, hopefully, but that can then inform models that other people apply to other regions, including Patagonia, Gulf of Alaska as well. I mean, every region has its unique geographic challenges, and obviously, for example, the flow properties of cold-based ice will be different. But and also this idea of, does a degree day model, what's the capability of more of the sort of degree day approach Batu's talked about versus a more formal energy balance? What are the pros and cons? And that we're really learning a lot more about that, I think, and also how we validate against independent observations. But I'll let Batu jump in here.
No, I was just going to say that, in addition to what you had mentioned, one of the other required outcomes, or that was in the proposal announcement, was that a set of tools would be generated for you in this analysis, and that they were to be made publicly available. And David Sheen is also a big proponent of that, and I believe he already makes his most of the tools that he makes the analysis with publicly available. And also other high mountain Asia teams are working towards making tools available. It's I'm hoping that these tools, at least some of them, will be applicable to other regions, especially in terms of remote sensing analysis tools.
Yeah, I think that'd be fantastic. I mean, certainly debatable, but arguably you've developed these sets of tools for the hardest set of or region of many glaciers. If you compare it against those other regions, I mean, you wouldn't have agriculture and much less debris cover to worry about in the Canadian Arctic archipelago. And certainly to a lesser degree in some of those other glaciated ranges you mentioned. So yeah, I think that would be fantastic.
Sure.
Cool. Any other questions from the audience?